Alright, so this is section 7.2, which is on matrices and linear system. So first we talk about a matrix function or vector function. A matrix function or vector function is just a matrix or a vector whose entries are all functions. So it's not a difficult concept, and if you want to take a derivative of a matrix or a vector function, all you need to do is to take derivative of every single entry. So we take entry-wise derivative. Right. So for example, if you take a matrix function, let's say cosine t, let's say sine t on top left, sine t, 1, t, cosine t, and we want to take the derivative with respect to t, then all we need to do is to take the derivative of every single entry. So this is cosine, 0, 1, and negative sign. So this is a matrix function. And if we want to take a vector function, let's say t squared e to the negative t, so this is a vector function, and we want to take the derivative with respect to t, then we take the derivative entry-wise. So it's 1, 2t, and negative e to the negative t. And all the usual derivative rules follow. So just to remind you, the derivative of the sum of two matrices is just the sum of the two derivatives. Nothing special. The derivative of the product of entry two matrices is still the product rule. So A times the derivative of B and B times the derivative of A. But remember to keep the order correct. Otherwise, matrix order matters in multiplication. So keep the order here. Okay. So let's what matrix or vector functions are. Let's talk about first order linear system. Okay, so previous section we talked about first order systems. Now we're going to talk about linear systems. So a first order linear system looks like this. So you have n functions, x1 prime, x2 prime, all the way to xn prime on the left hand side. On the right hand side, you have a linear combination of x1, x2, all the way to xn. So with coefficient. So here we have coefficient. It's a function of t times x1 of t plus p12 of t times x2 of t plus all the way to p1n of t times xn of t. And you also have the constant term, which is a function of t. So f1t and p1, now 1, 2, 2, 1 here. So the same thing for every single row. Give me 1 second here. A bunch of dots here. Pn1, x1, pn2, x2, plus all the way to pnn, plus fnt. Okay, but we know how to efficiently write a system of linear equations in terms of matrices and vectors. So this is not an effective way to write it. So if we take what we have learned before, the left-hand side is just a vector. So this part is just a vector. x1, I'm not gonna x1 prime, x2 prime, all the way to xn prime. So this is the left-hand side. The right-hand side, this middle part is the product of a matrix and the function. So the matrix, it has coefficient p11, p12, p1n, p21, p22, p2n, pn1, pn2, pnn. And the vector you're multiplying by is the vector x1, x2, all the way to xn. And then you have the constant term. This is the constant term. f1, f2, Fn. Okay, so that's one way to write it. And if we call this thing x vector of t, it's a function of t, it's also a vector. If we call this thing xt, then this is xt, but the derivative of xt. So that's a prime here, and let's just call this giant thing p. This is a matrix, so let me put boldface here, p of t, and this is f of t. This is a vector. Okay. So now we have the equation x prime equals to p times x plus f. So p is the coefficient matrix, technically matrix function, and f is the constant term. Yep, so we have rewritten this first order linear system in terms of matrices and vectors. And this system, the system that is homogeneous. It's homogeneous if the constant term is 0, so if f is the 0 vector. Okay, so we're gonna first just discuss homogeneous systems for now. Okay, so before we talk about solutions, we first have to talk about independence of solutions. So let's do that. So independence of solutions. Okay, so suppose x1 vector, x2 vector, xn vector are solutions of a homogeneous first order linear system of n equations. So suppose we have n solutions, we want to check if they're linearly independent. We also have the Wronskian to determine whether they're independent. So their Wronskian is defined to be W equals to the determinant of a matrix. The first column is x1, the second column is x2, and the nth column is xn. This is a n by n matrix function. Notice that there's no derivative here, just x1, x2, all the way to xn. This is their Wronskian. So there are two cases. If they're dependent, are linearly dependent, then the Wronskian is always 0. And the other case is if they are linearly independent, then their Wronskian is never 0. All right, so that's about independence of solutions. And now we have a general theorem. So this is a big theorem. So suppose we have a first order linear homogeneous linear system of n equations. So if you have a first order homogeneous linear system of n equations, then it has n linearly independent solutions, x1, x2, all the way to xn. So if you have n equations, then you have n independent solutions, and a general solution is a linear combination of these n independent solutions. So a general solution is of the form c1 times x1 plus c2 times x2 plus all the way plus cn times xn. Okay, so that's the general solution. And if you have initial conditions, so given initial conditions, So it's first order, so we only need condition at 0 for each function, but there are n functions, so we have n initial conditions. So given initial conditions, x1 at the number equal to b1, x2 at the number equal to b2, xn at the number equal to bn, that the particular solution is unique. So notice that these x1s and these x1s are different. These x1, x2, xn's, these are vectors. These are vector functions. And these are just entries of the vector functions. So be careful, they don't mean the same thing here.